Hello, brilliant students. Today, we'll explore what factors influence the rate of a chemical reaction. Imagine baking a cake. If you increase the oven temperature or add more baking powder, the cake might bake faster. Similarly, in chemistry, changing the concentration of reactants, pressure, especially for gases, temperature, or adding catalysts changes how quickly reactions happen. For example, when you spray perfume, the scent spreads faster at higher temperatures. Catalysts are like expert chefs that speed up reactions without being used up. Isn't it fascinating how tweaking these conditions changes the speed of chemical transformations? So, fasten your seatbelts as we dive into what controls the reaction pace in the chemical world. Now, before we proceed, think about this. If you double the amount of reactant in a reaction, what do you think will happen to its rate? Pause for 15 seconds and ponder this. Welcome back, everyone. Let's build on what we discussed. The reaction rate's dependence on reactant concentrations is captured by something called the rate law, or rate expression. Think of it like a recipe that tells us how much each ingredient concentration influences the cooking speed. But here's the twist. The powers to which these concentrations are raised, called reaction orders, don't always match how many molecules you see in the balanced equation. Just like in cooking, sometimes you need double the spice for just a little taste change. We'll discover how each reactant concentration contributes to the rate, which helps us predict and control reactions effectively. Ready to see the magic formula? Let's explore that next. Let's delve deeper into the powerful rate law that chemists use to understand reaction speeds. Consider a general reaction where A molecules of reactant A react with B molecules of reactant B to form products. The rate law tells us that the reaction rate is proportional to the concentration of A raised to some power, x, times the concentration of B raised to y. Here's the formula. Rate equals K, the rate constant, multiplied by A raised to x and B raised to y. For example, if x equals 1, doubling A's concentration doubles the rate. If x equals 2, doubling A's concentration quadruples the rate. Remember, these exponents, x and y, tell us the sensitivity of rate to each reactant, and they are determined experimentally, not just by counting molecules in the balanced chemical equation. Also, the negative derivative term indicates that the concentration of reactants decreases over time. So reactions slow down as reactants get used up. Now, observing equation 3.4 on your screen, notice how each part fits in this rate law framework. Take a moment and imagine if the exponent on A was 0. What would that signify for the reaction rate? Think for 15 seconds. Here we see a fascinating example with the reaction of nitric oxide, NO, and oxygen, O2, forming nitrogen dioxide, NO2. Table 3.2 on your screen shows how changing initial concentrations of NO and O2 impacts the rate at which NO2 forms. Look carefully. When no concentration doubles from 0.3 to 0.6 molarity, with O2 constant at 0.3, the rate quadruples from 0.096 to 0.384 mole per liter per second. This means the rate depends on the square of no concentration. That's a second-order dependency for no. On the other hand, doubling O2 concentration from 0.3 to 0.6 molarity while keeping no constant doubles the rate from 0.096 to 0.192, indicating a first-order dependency on O2. As a result, the overall rate law for this reaction is rate equals K times NO squared times O2 to the first power. This experiment is a beautiful example of how chemists uncover reaction mechanisms by careful measurement. Now take 20 seconds to examine Table 3.2 and see if you can predict what happens if both NO and O2 concentrations are doubled, as in Experiment 4. Chemistry is full of interesting surprises. For example, look at the first reaction on the screen. Chloroform, CHCl3, reacts with chlorine gas, Cl2, to give carbon tetrachloride and hydrogen chloride. Its rate expression shows the rate depends linearly on chloroform concentration, but only on the square root of chlorine concentration, meaning the reaction speeds up less sharply as chlorine increases. Now look at the second reaction, the hydrolysis of an ester with water. Its rate depends on the concentration of the ester, but is independent of water's concentration, indicated by an exponent of 0 on water. This happens because water is in large excess, so its amount effectively remains constant during the reaction. So we learn that reaction orders reveal the nuances of chemical kinetics and are experimentally determined. Always remember, just seeing the balanced chemical equation won't tell you the reaction order. Experiments are the true guide. Let's pause for 15 seconds. Why do you think water's concentration doesn't alter the rate in the ester hydrolysis? Something very important to note, students. Reaction orders, the powers to which concentrations are raised in the rate law, do not necessarily match the stoichiometric coefficients from the balanced chemical equation. That means you cannot just look at the chemical formula and guess how the rate depends on reactant concentrations. Real-world measurements and careful experiments are essential to find the true order. For example, some reactions are zero order with respect to a reactant, meaning changes in that reactant don't affect the rate at all. Others might have fractional orders, such as 1/2 or 3/2, reflecting complex mechanisms. Think about it like different drivers tuning the same car. The effect varies depending on who's behind the wheel. Now, let's explore how to find the overall order of a reaction from its rate law. Great job keeping up! Now, let's unlock how to find the order of a reaction. Each exponent in the rate law, like the ones you see here on your screen, shows the order with respect to each reactant. The overall order is the sum of these powers. For example, in the first rate expression, the power of A is 1/2, and that of B is 3/2. Adding gives an overall order of 2. In the second example, B has a negative exponent, meaning increasing B slows the reaction. The overall order is a fractional 1/2 here. This means the reaction is complex, and these fractional orders tell us something deep about the reaction mechanism. Remember, order influences how sensitive the rate is to concentration changes. Can you think of a real-life scenario where increasing something can slow down a process? Pause for 20 seconds and reflect. Now let's talk about molecularity, a key term that describes how many reactant species come together in a single elementary reaction step. If only one molecule breaks apart or rearranges, it's unimolecular, like ammonium nitrite decomposing into nitrogen and water. When two molecules collide and react, it's bimolecular, such as hydrogen iodide dissociating into hydrogen and iodine gas. Sometimes, but very rarely, 3 molecules must collide simultaneously to react. Trimolecular reactions, which are slow because 3-way collisions are uncommon. Picture 3 friends needing to meet at exactly the same corner at the same time. Very tricky. Keep in mind, molecularity only applies to single-step reactions. Complex reactions go through many steps, and molecularity is assigned only to these elementary steps. Ready for more fascinating reaction kinetics? Let's explore how reaction rate and molecularity relate through reaction mechanisms. Imagine a relay race with a team of runners. The overall speed depends on the slowest runner, right? Just like that, Complex reactions happen in multiple steps. One of these steps is the slowest and controls the entire pace of the reaction. We call it the rate-determining step. For example, the decomposition of potassium chlorate KClO3 involves several steps, but has an overall order much lower than it appears from the balanced equation. Reaction orders come from this rate-determining step's molecularity. So, uncovering the mechanism is like solving a detective mystery. Which step slows everything down and sets the rate? This understanding helps chemists design better catalysts and optimize conditions. Now let's look at a real-world example of a reaction mechanism involving hydrogen peroxide catalyzed by iodide ions. Let's explore a classic example of reaction mechanisms and catalysis. Hydrogen peroxide decomposes into water and oxygen gas slowly on its own. But with iodide ions as catalyst in alkaline medium, the process speeds up dramatically. The overall reaction is two hydrogen peroxide molecules decomposing into two water molecules and oxygen gas. The rate depends on the concentration of both hydrogen peroxide and iodide ions, making the reaction first order in each. The mechanism occurs in two elementary steps. First, hydrogen peroxide reacts with iodide ion to produce water and IO intermediate. This step is slow and controls the overall rate. Then IO rapidly reacts with another peroxide molecule to regenerate iodide and release oxygen gas. Isn't it fascinating how the catalyst cycles, never consumed? Think of it like a helpful assistant speeding up tasks without tiring. Now take 20 seconds to think. Why is identifying the slow step crucial in understanding reaction kinetics? Understanding the units of the rate constant K is crucial when working with reaction rates. The units depend on the overall reaction order, which is the sum of the powers of reactant concentrations in the rate law. Look at the formula. Rate equals K times concentration raised to the nth power. Rearranging gives K as rate divided by concentration to the order n, so units of K compensate accordingly. For zero-order reactions, K has units of molarity per second, mole per liter per second. For first order, it's simply reciprocal seconds per second. For second-order reactions, it's liters per mole per second. Table 3.3 outlines these units clearly. This helps chemists check that their rate expressions are consistent and allows easy comparison between different reactions. Now, consider this question. If a rate constant K has units of s to the power of -1, what is the likely order of the reaction? Pause for 15 seconds and think. Measuring how fast reactions happen at an exact moment, what chemists call instantaneous rate, can be tricky. It's like trying to measure how fast a car speeds up at a precise second while driving. To avoid this, scientists use integrated rate equations which directly relate how much reactant is left after a certain time. This way, instead of guessing from slopes, we use concentration measurements at different times to understand kinetics. Today, we'll focus on the integrated rate laws for zero and first-order reactions, which are the most common in chemistry textbooks and labs. These equations allow us to predict concentration at any time, or find the rate constant based on changes in concentration over time. Looking at the curve on your screen, think about what kind of graph you'd get if reaction rate stayed constant during the reaction. Pause and imagine for 15 seconds. Zero-order reactions are unique in that the rate stays constant no matter how much reactant you have. Mathematically, the rate equals the rate constant K with no dependence on concentration. When integrated, this yields a simple straight-line equation. Concentration of reactant equals initial concentration minus K times time. So, Plotting concentration against time gives a straight line slanting down. The half-life in zero order depends directly on the initial amount you start with, meaning the more you begin with, the longer it takes to halve. For instance, the decomposition of ammonia gas on a hot platinum catalyst, as shown, happens at zero order at high pressure. Even if you add more ammonia, the rate won't change because the catalyst's surface is saturated, like a crowded platform at a train station. This concept helps understand surface reactions and catalysis. Look at Figure 3.3 and see the linear drop in concentration over time. Now, can you think why a metal surface could cause zero-order kinetics? Think for 20 seconds. First-order reactions are the most common type you'll encounter. Here, the reaction rate depends linearly on the concentration of one reactant. The integrated rate law transforms the differential form into a handy equation. Natural logarithm of concentration equals minus k times time plus the natural logarithm of initial concentration. Plotting ln r versus time yields a straight line where the slope is negative rate constant k. This simplification is powerful for analyzing experimental data. The half-life in first-order reactions is special. It's constant and independent of initial concentration, given by 0.693 divided by K. For example, the decomposition of dinitrogen pentoxide, N2O5, is a first-order reaction. Given initial concentration and concentration after 60 minutes, chemists can calculate the rate constant. Figure 3.4 illustrates the characteristic linear trend. Now, as a challenge, if the plot of natural log of r versus time is not linear, what might that imply about the reaction order? Pause for 20 seconds. Let's wrap up our deep dive into reaction kinetics with this summary table, Table 3.4, which compares zero and first-order reactions. Zero-order reactions have a constant rate independent of concentration. Their reactant concentration decreases linearly with time, and half-life depends on how much you start with. First-order reactions depend linearly on reactant concentration. Reactant decays exponentially and have constant half-lives independent of starting amount. Look at the types of plots to analyze kinetics. Plot concentration versus time for zero order, and natural log of concentration versus time for first order to get straight lines. Units of rate constant K vary accordingly. Use this as your go-to guide when analyzing reactions. As you proceed with studies or labs and collect data, this table will help you quickly deduce reaction orders and constants. Now, imagine you're a scientist trying to classify an unknown reaction. What steps would you take to figure out the order experimentally? Pause for 20 seconds and reflect. To finish, let's talk about an interesting case in kinetics: pseudo-first-order reactions. Sometimes a reaction is theoretically second-order, involving two reactants. But if one reactant is present in huge excess, its concentration barely changes during the reaction. This causes the reaction to behave as if it were first order with respect to the other reactant. A classic example is the hydrolysis of ethyl acetate with a large amount of water. Since water is so abundant, its concentration remains almost constant, and the rate depends mainly on the decreasing ethyl acetate concentration. This simplifies calculations and experimental analyses significantly. Scientists often exploit this to study complex reactions more easily. On the screen, you see how the moles of water barely change compared to ethyl acetate during the reaction. Reflect for a moment. How might this concept be useful in designing experiments? Pause for 20 seconds.